All right, my name is Madison Baji, and this is my Module 3 presentation. First off, I want to introduce the data set that we're working with here. We had, in this scenario, 30 participants, and we're going to say that we had them answer 2 different surveys. As you can see, we have a number of variables off to our left side. We have Y1 through Y4. In this case, we are saying that we had our users answer a usability questionnaire. So those 4 are going to be our 4 usability questions. Those are going to be our outcome variables. We want to see how different things might affect the overall usability scores users are giving our products. You can also see that we have variables x1 through x7. These are going to be different items from our questionnaire that may affect our overall usability scores. And you can also see variables F1 through F8. This is a different category of variables. These will be our dummy coded responses. These might be things that we can group users by, like gender or the frequency of use, like how often they use a product rated on a Likert scale, maybe something from 1 to 5, something that is not necessarily scale, but in individual increments. And you can see here we have an overall summary of our data, giving different means and standard deviations, so you can get an idea of each variable and what that might look like as we go to further analyze them. So one way that we might do that is to do a regression. We might want to see how one of our variables affects our overall usability scores. So to do that, we might look at doing a regression. In this case, we might look at a simple bivariate regression. We might see how one variable interacts directly with another variable. And to do that, we'll might take a look at that a little closer. We'll have some sample data here that we just made up, which you can see we've already calculated our means for here. That way we can get us going. If we go on, we can calculate our deviation scores from those means. And we can use those and find our sums of our squared deviation scores, which allows us to calculate our overall variance for these 2 variables, which you can see we have done here at the bottom. Remember, our variance is just those squared deviation scores over our degrees of freedom. We can then take that to find our overall covariance, which is just a measurement of how our x and y vary together. We can take the sum of all of our x's multiplied by all of our y's minus the product of our means and our n, and we put that over our degrees of freedom. And you can see here our overall covariance is 5.5. This, having all of these numbers together, allows us to calculate our full regression equation. We can find our slope, which is this, our B1, in this case, which stands for beta 1, but we'll call it our slope for now since we're just looking at a bivariate regression. We can find our slope, which is just going to be our change in y for every 1 unit change in x. And we can do this by dividing our covariance by the variance of x. In this case, you can see we get a 0.60 as our slope. And we can also find our y-intercept. This is going to be our v0. We can do that by taking our y-mean minus our slope multiplied by our x-mean. As you can see that we've done that here. In this case, we see that our intercept is going to be a 2.4. We can plug both of these numbers back into our equation and get our final regression, which is going to be that y equals mx plus b, since we've all known since algebra in middle school. In this case, we have our y is equal to the 0.6x. That 0.6 again is our slope in this case, and then 0.2.4, which is our y-intercept. And we can use that to find our prediction for any data point that we may be given. In this case, we just have the one predictor and we only have one beta coefficient. which is, again, this is our slope. This is just our change in y for the 1 unit change in x. Different wording, all the same thing. However, we can go on to add more predictors and get a better idea of what our outcome variable y might be. So we can go on and do this with our questionnaire data. First, we need to check that multiple regression is a suitable choice at all for our analysis. And to do that, we should check that we meet all of the assumptions for multiple regression. As you can see, there are a couple of them. First, we have to assume that the relationship is actually linear, not parabolic, or in this case, this would be called curvilinear. Linear relationship we would refer to as rectilinear, same thing. We can also assume that the predictor makes sense for the outcome. If not, this would be called an error of commission, where we would be attributing the wrong predictor to the outcome. We can also assume that we don't need other predictors to account for our outcome. We're not leaving anything out. This would be called an error of omission. And we can also assume that there would be no measurement error. We're assuming that we are measuring everything just like we say we are. We're saying that our tools are good and we know how to use them accurately. These are all things that are kind of built into our overall study design. So these are things that we can check off right away. We can also assume that residuals are all equal to 0. And if not, our data might not truly be centered around the line we've chosen as our best fit. If that is the case, adding all of our residuals together would give us 0. If it doesn't equal 0, we may not have the best line of fit. We also need to assume homoscedasticity, which is a very big word, to just say that we have equal variance across the board. If we have unequal error across our data, unequal variance, that might indicate that our standard error may be biased and we might need to go back and reassess. We also want to make sure that we have no autocorrelation, which again is a big word, but that's just saying that our error terms of our observations shouldn't be correlated with each other. Basically, we're trying to avoid redundancy here. We can also try to assume that our predictor can't be correlated with our error term. Again, we're just checking all of our bases. And we should also try to ensure that our errors are normally distributed. If not, we may have something skewing our data collection. And again, we might need to go back to the drawing board and reassess how we are laying out our study design here. We can check a lot of these assumptions by plotting the data and taking a look. R gives us these nice 4 plots. We can look at these and assess a lot of those assumptions right off the bat. At least the ones that we haven't already addressed from the design of our study alone. If you look at this first graph here, the residuals versus fitted, this helps us look at how our error is distributed. And you can see that we don't have any major points of interest here. It looks pretty even across the board, which is a good thing for us. I do want to draw your attention to the several points that are labeled here. We'll get to those in a minute, but I want you to see these numbers appear across all of our graphs here. We can also look at the QQ plot up here in the upper right. That helps us check for normality by comparing our residuals to a normal distribution, which is that dotted line in the middle, and you can see just how far off our own data points are from that. Again, you see these points 14, 20, and 26 that are pulled out of the bunch. Especially if you look at 14 here, it's way off base from that dotted line. So we right off the bat have something of a little bit of concern around those couple of numbers. But moving on, we can go on and we can look at our residuals versus leverage. Looking at those points of concern, this is going to tell us the most about those points. It's a good way to determine potential outliers. As you can see here, it has graphed our Cook's distance. That's going to be our red dotted lines. If you see points in these areas, immediately that's going to be a point of concern. As you can see, that number 14 that I had already pointed out is well within Cook's distance. We also have those other few points, 26 and 20, that we are pulling out of the bunch. And again, those are points of interest we might want to consider removing as they might be outliers that are skewing our data. So we might want to remove those, but we still have another problem. We also need to check if our predictors are correlated with one another because, again, we want to avoid that redundancy. If we do a correlation analysis against all of our correlates, we didn't find any correlations between, say, 1 or 2 or 2 and 3, but we did, however, find that X1 and X3 were significantly correlated with each other, which is a bit of a problem for us because that's something called multicollinearity. It basically just says that these two are redundant with each other. In that case, we want to go back to our study design, and we might want to take one of these predictors off the board. We might be measuring the same thing here. We might want to look at how we've designed our questionnaire, and we might want to pull one of these, as we definitely don't need both. So that is an entirely separate issue. And we can probably choose the best measure of these two and toss the other one, and then try to reevaluate our methods from there. After all of that, after we've removed our outliers and take a look at this, we can finally take a look at our final regression equation. Here we can see at the bottom that's going to be y equals 0.24 for x1 and 0.17 for x2 and 0.35 for x3 minus our intercept point of 0.16. And each of those coefficients, all of that saying that those are our beta coefficients. We're seeing that under the estimate column. That's going to be our first thing that we see here. That's just, again, saying how much our y changes with a 1 unit change in the variable it's associated with. So x1, x2, x3. These are our, quote, slopes for our individual variables. This is how we measure the changes for each of these variables and how it affects our outcome. Using our summary, we can see that none of these predictors are very good. And again, we had that multicollinearity with x1 and x3. So we can pretty much predict that. You can see that we have dots here getting close to significant, but they're not significant. And I feel like we would probably see a lot of difference here if we took one of those two out and replaced it with maybe another informative variable. So say we want to verify all of this using a different method. We could find out the same thing using ANOVA, as it's based on the same linear model. Both give us an omnibus hypothesis test with a focus on variation in our model. So, and we can see that just by looking at the core assumptions of ANOVA. They're really similar to multiple regression. You can see one of the top ones is independence. We want to make sure all of our data is independent of one another and that they're not interrelated. We also want to make sure that we have normally distributed residuals. Think back to our QQ plot for our multiple regression plots. It's the same thing. We also are wanting to look at homoscedasticity again, which is just saying that we want to be sure that we have equal variance across the board as we go to analyze this. And like we did with multiple regression, we have ways to analyze this with ANOVA as well. Here we did a Levene's test on our ANOVA model. This is just to check for homogeneity of variance. Again, big words, just saying we have equal variance. And you can see here, if we look at our p-value, we have a 0.6694, which is nowhere near significant, so we are good. Significance in this case would mean that we have a significant difference in our variance, which is not something we want. So in this case, non-significance is a good thing. We also ran a Shapiro-Wilk normality test. This is much like our QQ plot. It's analyzing our normally distributed residuals. As you can see, we don't have a significance there either, which in this case is good for us. So if we break down what it is to do an ANOVA, we can see here, this is our calculations by hand, that we can calculate our variance just like we did with regression. And what we do with ANOVA is we compare them between different groups. So in this case, in this example, we have some random data that we made up. Say that we have two groups and we want to look at how those two groups, maybe they're a different treatment for depression scores. Maybe one group goes to therapy for a week and the other one doesn't. And we also want to look at how gender may be affecting depression scores, if one group may be more predisposed to depression than another. So in this case, we have two different factors that we're looking at for our ANOVA. We have our group treatments as well as our gender groups, and we're wanting to look at how each of those affects our overall depression scores. You can see here that we calculated the means so that we can calculate the variance, much like we did with our regression. And in the same way, we can use that variance and we will look at it in an ANOVA table and compare them between groups. Here we can see our ANOVA table. This compares the sums of squares for each term as well as an interaction term. As you can see here, in this case, we don't have any significant predictors. If we're looking at our F values, we don't have any significance with our predictors in this case. In this case, that would be our different treatment groups, gender, and we didn't find an interaction between the two. This is just an example. Let's try to do this with our actual usability questionnaire to see if we have anything significant there. But we can see again, apologies, that's an old slide. We can see here that we chose two of the demi-coded variables. Say this might be gender and a certain focus group, and depending on which group you're in, see if that affects your opinions on the overall usability scores afterwards. Why not? As you can see here, though, we don't have significance with those two variables. Much the same as our linear regression, we were looking at two other variables, but we have not been able to find anything that predicts our significance for our usability scores. So overall, this may tell us that we might be focusing on the wrong things altogether. We might not be measuring what we think we're measuring. We have some problems with multicollinearity. We might want to rethink the variables that we're including in our models to see what might predict and what may not predict. This would probably mean that we need to go back to the drawing board and reevaluate our overall test design in this case, and make sure that we are measuring the things that we need to be measuring, and make sure that we are including variables that we think might be independent from one another and also tell us something new about our overall scores. And that's all I have. Thank you very much for a great semester.